Hello YouTube, RJ. Okay, so here's the finished, predominantly finished thermal test cell. You can see the box is done. Let's look at the back here. You can see we've got a pass-through for RF, so we can do frequency monitoring or send RF in if needed. We've got power for the system that runs the Arduino and temperature sensor and communication, our USB cable coming out. And the lamp for heating, we've got input for it separately so that it turning on and off doesn't affect voltages, and we can run different voltages if we choose to or whatever. Then we've got another set of pass-throughs here, which I'm going to add, and that's why I said predominantly done. I'm going to add another set here, and you'll understand why in a minute. But if we take a look inside, you can see we've got a foam insulated lid. You can see how I was showing the double boxes with the insulation between them. So this thing is insulated with closed cell foam all the way around. It's fairly well insulated. And you can see, if we get a good view here, you can see how these pass-throughs come through. And what that's for is it lets me clip alligator clip leads on, like that. Okay. These two are power and ground to run the device under test. Passes the 13.8 volts in. So you can put a regulating circuit of anything you want on the circuit. You can see the temperature sensor here in the corner. And of course the RF cable to pass RF in and out for testing oscillators and such. And so basically it's that. Like I said, I'm going to add another set of these, and the reason is as I started out building this test cell to test oscillators, as I said earlier, the main point was testing oscillators, but I also want to be able to test other components. So I started working on software to automate this, and so what I've done is I've got the software where it can use my ON voltmeter, and we have a new guest on the bench, or a new permanent resident on the bench. I've bought a Owen switch mode 60 volt 10 amp 300 watt power supply. Now I've got my trusty GW Instack GPC 3020 up on the bench up here, which you can't see at the moment, but that's my main go-to power supply, linear power supply, like quieter than a switch mode power supply. But this power supply has a purpose having to do with this. I'll use it for lots of things, but the main purpose that I bought it for was I wanted to be able to test things where I pass a control voltage into a test circuit and control it from the computer, and this does. And that allows me to send in varying voltages, voltage sweeps and such, to test equipment under different voltages. I've integrated the LCR meter that you've seen earlier videos where I purchased it, and so that's all integrated into the software, which I'll show in a minute. And it's very, very simple. It's just some Python. Command line interface, basically answer questions. It creates a test. You run the test. It logs all the data. Bam, you got a graph. You got all the information you want. So I thought, now that we've got this done, maybe we would do a demonstration of how we can use it. So what I'm going to do is I'm going to go ahead and I am going to hook up power, and I'll turn it around backwards here where you can see. And what I'm going to do is I'm going to hook up power, and we'll power it up, and I'll show how you set it up to do a test, and then I'll show you the results and show you, we'll go over to the software, we'll set up our test. Here's our system voltage from the power supply. And this is for the heater. And got that set up. And then in this case, I'm going to be measuring capacitance. So I'm going to connect up my LCR meter. Now I'm going to calibrate my LCR meter. That takes a good 2 minutes. I'm not going to make you sit and watch for that. I'll come back in a minute and we'll hook it up. We'll power everything up. We'll jump the computer. I'll show you the software. We'll set up a test and we'll run a test on an item. And then you can kind of get an idea of what I've built this for. Okay? Be back in a minute. Okay, with that I've got the meter calibrated, the LCR meter calibrated. The reason it took a minute, I had to get the probes and hook them up. You want to calibrate your LCR with these extra probes on because it's going to affect the readings. And so now that they're calibrated, let's say, for example, maybe we had a variable capacitor. We're just going to use this as an example, variable capacitor that we wanted to characterize. We wanted to say, how does this thing react to temperature? Okay. So what I can do is hook it up, put it in here. And in this case, we're just messing around, but I've set the capacitor, let's see, about, I'm going to say about half. So let's just for our example here. So what we do is we put our capacitor in the box and make sure we get our probes in. And our meter is reading 161 puff. Actually 161.3 puff. So now what we do is we're ready to test. All we have to do is we put our lid on, power supply, it'll make a little noise. You'll hear a USB kicking in on the computer over there. And now I'm going to pick up over on the computer and run through the software and show you what we're doing on the software and start this test. Okay, so we're on the computer now. We're going to start our Python little program we wrote here. It's going to want to know a file name. I'm going to call it variable capacitor temp test. How many number of minutes to run the test? We're going to do 120, 2 hours. We want to give it plenty of time to stabilize and come up to temperature and be stable. Let's do 10 seconds for our sample rate every 10 seconds. We are going to apply heating. Yes, that's going to turn the heater on and warm it up. We want it to increase 20 degrees C. We want 1 minute delay. We do not want to measure frequency. We do not want to measure voltage at this time. We do want to measure LCR. We do not want to apply a fixed voltage, and we do not want to apply a variable. And it should take off, and it's starting to log. And you can see the date and time here. You can see that it's 0 seconds into the test. The heater is off. The capacitance is 170.7570 puff, and 29.4 is the temperature. So it's going to go for 49.4. It's going to be its target. So we'll watch here for a minute. It should kick the heater on at that point, and we'll let it log for 2 hours. We'll come back and I'll show you the outcome of testing this variable capacitor. Okay, it's back. It's been a little over 2 hours. Test is finished. I'm back at the computer, and so let's pull up and look at our data here. So we've created our data for our 2 hours, and so if we go over and chart that out and take a look, we come up with something that looks like this. As you can see, the temperature started out around just a little under 30 degrees. Heat kicked in 29.2 degrees Celsius and rose fairly linear, not perfectly linear, but fairly linear up to 49 point, around 49.1 or so, which was our starting temperature. I think was 29.4. Let's see if I can get the very first point here. 29.4. So we were shooting for 29.4 plus 20, which would be 49.4. So as you can see, we reached and kind of bobbled along there as the heater kept turning on and off to keep the temperature. Did a fairly good job. We can see capacitance started out about 170.75 roughly. And you can see that it kind of stabilized at the end here. That's why I run out a full 2 hours. And we ended up about 171.6 basically. So, you know, you're only looking at a 0.9 puff change here. And so that might seem insignificant. But let's take a look at, let me bring over a LC resonant frequency calculator from the web. What I've done is I went ahead and put the starting capacitance in there and then figured out the inductor to get you around 7 megahertz. And so my thought was, you know, let's take this and let's change it. This is our starting frequency. We've got our radio tuned here, and then our capacitor, variable capacitor, drifts to 171.6. What happens? Well, you can see you're way off frequency now. In fact, let's go back and figure that out again. 170.75. Let me get my calculator over here. Okay. So here's a current frequency. And let's subtract this frequency. Over 17 kilohertz. Just that small change would create this kind of change. So, you know, these components do matter. And obviously, if we're going to use this to control the frequency of an oscillator, 17 kilohertz is not going to work, drift in that temperature range. While you don't expect it to change suddenly that much temperature, it shows that the frequency will drift with very little temperature change, very little capacitance change here. So based on that, we're going to have to do something to offset this variable caps drifting, and there's a lot of ways we can approach that, but this was more just to show the test cell, how it works, what we'll be using it for. So I hope that was entertaining and informative. So thank you for watching. Hopefully you find this interesting. If you do, hit like, subscribe. That helps me get more people to the channel and makes it worth my time to create this kind of content. Hopefully you'll find interesting. So now that we've got the test cell done and we've done a test with it, shown that it'll work, following videos are going to show some tests where we're actually going to run some things and compare stuff. One of the things we're going to do in a coming video, probably the next video after this, will be we're going to try creating a number of inductors using different cores. And we're going to find out if the core makes a difference in drift over temperature. The temperature coefficient, if it's, you know, a type 6 is better, maybe a type 7 is better, compared to a type 2, compared to, you know, we're going to try some of these different types and see which one holds its inductance values more accurately with temperature change. So again, thanks for watching. I hope to see you again.